Machine learning methods can be broadly classified into three different kinds of learning methods: supervised learning, unsupervised learning, and reinforcement learning. The difference between these three methods have to do with the teacher in the learning approach. Whether or not there is a teacher, which in machine learning is known as a supervisor, and what kinds of information that supervisor is allowed to give to the learning algorithm is what defines the difference between supervised, unsupervised, and reinforcement learning. In supervised learning, the supervisor, acting as the teacher, gives each picture or each piece of data a correct label. The learning algorithm not only gets the data in order to learn from, it also gets the label given by the supervisor. The task of the learning algorithm is to learn a mapping from the features of a picture to a label or a class. Here, the term class refers to a group of labels. For example, this picture over here has the label dog. Dog is a class that applies to a set of different pictures. So in supervised learning, the robot or the learning algorithm gets both the picture and the labels that have been assigned by the supervisor. In unsupervised learning, there is no supervisor, and because there is no supervisor, the robot does not have the labels that go with each picture. Instead, the robot has to figure out the labels that go with each picture by grouping pictures that are similar. In unsupervised learning, the robot may start out by knowing the number of groups that it is looking for, but it does not know which labels go with which pictures. Reinforcement learning is a method that is partway between supervised and unsupervised learning. In this method, there is a supervisor that gives information to the robot, but the supervisor does not give labels to the learning data. Instead, the supervisor can only tell the robot whether it is correct or incorrect in each decision that the robot makes. The robot can then use the information from the supervisor about which decisions were correct and which were not correct in order to update its classifier. Classifier is another word for a learning algorithm. Each of these different types of learning methods, supervised, unsupervised, and reinforcement learning, have different methods that fit within each category. Here, we're going to look at just a few of the methods that are the most common or the most useful generally within each category. Within the supervised learning category, we're going to look at two specific methods, one called support vector machine and another called artificial neural networks. Within the unsupervised learning category, we will look at one method called k-means clustering. And within reinforcement learning, we'll look at one method called exploration versus exploitation utility maximization. We'll start out by looking at the supervised learning methods. The first supervised learning method we'll look at is called support vector machine. This approach is an optimal way to divide two classes of data. So, for example, if we're just trying to tell the difference between dogs and horses, or between rabbits and dogs, then this might be a good method to use. Now, support vector machine is a type of supervised learning. So in this approach, our robot is given a set of training data already with labels attached to each picture, which were assigned by the supervisor. We can picture this data with labels assigned on a feature plot as shown here. I've shown data points taken from the rabbits and labeled as rabbits in blue on the feature plot. And I've shown data points taken from the dogs and labeled as dogs by the supervisor as red data points. We will give the support vector machine algorithm as its input both the feature values of each data point and the class which each data point belongs to. So the support vector machine input might look like this. It will be a matrix where each row of the matrix is one data point. Each column of the matrix represents one feature value. So we have feature 1 in column 1, and we might have feature 2 in column 2. We also need a column that holds the label. For example, suppose that we have a bunch of pictures of horses and dogs. And let's suppose that feature 1 is height. And feature 2 is width. We also have to assign a number to each label. For example, we might have the label 1 representing horses, and the label 2 representing dogs. One animal picture gives us one data point, which gives us one row of the matrix. If this animal is a horse, it will probably be taller and wider than a dog. So we might get a row for a horse that looks like this. While for a dog, we might get a row that looks like this. If we then have another horse, we might have a row like this one, and another row for a dog might look like this. This matrix, consisting of all of our training data, giving the values for feature 1, feature 2, and the label assigned to each data point, is the input to our support vector machine. The support vector machine produces an output that is a line or a plane, depending on how many dimensions we have in our feature plot, that optimally separates the data. In other words, this line is positioned equidistant from the two classes of data. Once the robot has found this line that optimally separates the two classes of data, we no longer need this training data. We can go and get the testing data and test how well this robot has learned this information. Here, the training is completed. After the training is completed, a new animal is seen from the testing data, and the features are extracted from that data point in the testing data. If that data point falls on one side of the line, it will be classified as a dog. If it falls on the other side of the line, it will be classified as a rabbit. Note that this method can be used regardless of the number of features that we have available. I've shown a two-dimensional example because it's easier to draw in 2 dimensions. But we can also do this if we have 3 or 5 or 10 or any number of features available. So let's consider for a moment how well support vector machine works. Will the robot always learn animal classifications correctly? Whether or not the robot will correctly learn these classifications depends upon many different factors. One of these factors is what's known as separability. Support vector machine will not work very well if the data are not separated from each other. For example, we would expect support vector machine to do a good job with data like this. This data will be considered to be separable. By separable, we're referring to the distance between the data, or the amount that the two classes of data are distinct from one another. Here's an example of data that are non-separable. Notice that the two classes of data, the red points and the blue points, are not distinct from one another. They're interspersed. This is a case where we would expect support vector machine to not do a very good job of learning the difference between the two classes of data. Another issue for support vector machine to work well is the distance between the classes. If the two classes of data are very close, we would expect support vector machine to not do as well. A third consideration is the amount of training data and whether or not the training data are representative. Let me show you an example of what this means. Suppose that we have two classes of data shown here in red and blue, and we want to use support vector machine to find the separation between these two classes of data. If we give all of this data to the support vector machine as training data, the line that the support vector machine will find between these two classes is like this. And that line will do a good job of separating or of classifying future data points. Now, suppose that instead of giving all of this data to the support vector machine, we separate our data up into training and testing groups of data. Suppose that the points that we give for training in the blue class are these points. And suppose that the data points we give for training in the red class are these points. What separating line will support vector machine find here? Here, the support vector machine might decide that this is a good line that separates these two classes of data. In the future, when we see a new data point in the blue class that lies over here, we will misclassify that data point as being a part of the red class. Similarly, in the future when we see a red data point that shows up over here, we will misclassify that data point as being part of the blue class. In order for support vector machine to work well to separate classes of data, it's important that our training data that we give to the algorithm to learn the separation is representative of the actual data set. That we don't simply select points that fall over here or only in another area of the full range of data points, but we give data points that fall in all of the different ranges where those data points might fall. Another way that support vector machine can fail is if we select the wrong features. For example, if we try to tell the difference between dogs and horses, not with their height and width, but with, say, fur color, we might not do a very good job of finding the data to be separable, because horses and rabbits can both be brown or other common colors. Now, let's take a look at another method of supervised learning called artificial neural network. An artificial neural network is a method that is biomimetic. In other words, it imitates a living thing. In this case, the artificial neural network was built to imitate the structure of the brain. In this approach, we create a network of artificial neurons. Each neuron is a simple mathematical function that receives an input and produces an output, and that output becomes the input to other neurons. Here's a diagram that shows how an artificial neural network works. Each of these circles is called a neuron. The neuron receives an input, and that input is limited by a function. Sometimes it's a limiting function to prevent the output from growing too large. After that input is limited by the neuron, the output travels along one of these connections to another neuron, and the value is multiplied by some weight. After the value is multiplied by a weight, it's received by the next neuron. The next neuron limits the value again and sends it along the next link to the next neuron. and once again the value is multiplied by some weight. When a neuron has more than one input coming into it, the neuron starts by adding up all of the values that are coming into it. Then, that added up value is what gets limited by its limiting function. The numbers that come in at the start are the feature values that we've extracted for each data point. The number that comes out at the end is a number that corresponds to a class, like we saw earlier where we assigned a 1 to the dog class and a 2 to the horse class. Here's an example of how this works. We might start out with a number assigned to each class. For example, 1 is a rabbit, 2 is a dog, and 3 is a horse. The feature values of a single data point come into the two neurons. Each neuron limits the value with its limiting function, and then sends the value off along one of these links where the value is multiplied by a weight. Each of the receiving neurons adds up all of the inputs that are coming to it and limits that value with its limiting function and sends the output out again. The final neuron adds up all of its inputs and produces a class value. The first time we run this algorithm, it's likely that this neural network will not correctly classify the animal. For example, in this case, we've classified this input animal as 2.2, which would correspond to a dog. However, we know that we've misclassified the animal because this is a supervised learning method, where the supervisor can tell the algorithm what the correct answer should be. So the supervisor tells the algorithm that the animal is actually a horse, and we're able to calculate an error. 3, which represents a horse, what it should be, minus 2.2, the value that was actually calculated. The value of this error is then used to change the values of each of the weights on each of these links between the neurons. The next time this network sees this same horse, its classification will be closer to horse because we've changed the weights on each of these links. Over time, the values of each of these weights will come closer and closer to the values necessary to classify each of the possible inputs as the correct class. Often this requires that our neural network sees each of the training data points more than one time. But once the weights have settled on their final values, we can give a new picture to the network, a picture that the network has never seen before, and the network is able to classify that picture into the correct class. Let's take a look at the differences between the SVM, Support Vector Machine method, and the ANN, Artificial Neural Network method. The Support Vector Machine is optimal in the sense that it finds the best line in between the two classes. Artificial Neural Network is not optimal. It may do a much better job classifying one class of data points than it does classifying other classes. Support Vector Machine also does better with data that are linearly separable. That is, data for which it is possible to draw a straight line in between the two classes of data. The neural network, on the other hand, is better at dealing with data that's a little bit mixed up and not as separable. Also, because the neural network has to see data multiple times in order to learn the classifications, the neural network does not necessarily give the same answer every time, while the support vector machine does. Another effect of this is that the support vector machine is simpler and faster because it's able to learn classifications by seeing the data only one time. In the next video, we're going to be looking at the unsupervised and reinforcement learning methods.